Of course, the outcome of a random experiment doesn't need to be discrete. It could be continuous, right? You could be measuring someone's height, for instance. So there's more than two possible outcomes. In theory, at least, there's infinitely many different heights. We're going to talk about continuous random variables in general and make a link to calculus and expectation of a continuous random variable. Talk about some commonly used continuous random variables: normal distribution, the exponential distribution, the gamma distribution. Then we'll talk about joint distribution, which can be continuous or discrete or a mixture of both. Combine more than one random experiment together. And then we'll end by talking a little bit about how you can use some continuous random variable, particularly the normal distribution, to approximate computations for discrete random variables, such as the binomial distribution. Back in the days where nobody had access to computer software that could compute the cumulative distribution of a random variable, then it made sense to use these continuous approximations. Nowadays, not so much, because you can compute the required probabilities directly from the distributions, discrete distributions. But it's still sort of neat to see how the continuous distributions could be used to model binomial discrete distributions. So how do we approach probabilities when you have what I'm calling here uncountably infinitely many outcomes? If X, as I said, represents the height of an individual in the population, the outcomes of the random experiments, the measurements, in theory, will reside in some continuous interval. Now, in practice, we know that's not the case because of quantum mechanics. There is such a thing as the smallest possible distance that it is possible for us to talk about. And so there isn't an uncountable infinity of potential heights, right? Even in theory. But we model it as though every real number could, in theory, be someone's height within some reasonable interval. Like, you cannot have negative heights, and presumably, if you're talking about human beings, it is unlikely that you will ever go much taller than 7.5 feet, 7'9". I know there was a Robert Wadlow who was excessively tall, might have been 8 feet tall, 9 feet tall, but these are outliers for sure. At the very least, it's safe to say that nobody would ever be 10 feet or taller when you measure these things. In a discrete case, you compute probabilities using the probability mass function. It tells you what the probability is for the random variable to take on one of the potential discrete outcomes. It could be infinite, but still discrete. If you're working with continuous random variables, the role of the probability mass function is played by something called the probability density function. We still denote it by f at x, but one of the things you need to keep in mind is that f at x doesn't actually give you the probability that the random variable will take on the value x. The big difference between continuous variables and discrete variables. And we'll see one of the consequences when we talk about the values that the density function can take. The cumulative distribution function, the CDF, for any variable is still as before the probability that x would be smaller than some threshold of interest to you, little x, except now there's infinitely many outcomes. Whereas before, in the discrete case, we could, in theory, write, this probability here as, for instance, probability that is equal to 0 plus the probability that is equal to 1 plus and so forth all the way up to x, assuming you start at 0, but presumably you could also go to x equals -1, -2, and so forth. You can't do this with continuous variables anymore because there's infinitely many values it could take. It could take the value 1/2, it could take the value 3/4, it could take the value 1/2 plus 3/4, and so forth, right? And it's not just that it's an infinite number of values it can take, it's that this infinity is uncountable. So it's not sufficient to add a few terms of the form the probability that the random variable takes on a specific level. 5, 6, 8, 300, 5,000. That's not how it works. One of the things that we do know is that for continuous variables, the CDF has to go to 0 when x goes to minus infinity, and it has to go to 1 when x goes to positive infinity. And here it makes sense to speak of the limit. Let me draw this for you here. You would expect the CDF to look something like this. We don't know what's happening in between per se. It would look like this. The one thing we do know is that it's impossible for the CDF to sort of like turn. It has to be increasing throughout. We just don't know the rate at which it's increasing. Okay? And it makes sense to speak of limits because there's a continuous domain for the values of x. We couldn't speak of limits in the case of the discrete random variables. The limit is not defined. The link with calculus is pretty easy to make once you identify the relationship between the PDF and the CDF. The probability density function is just the derivative of the cumulative distribution function. You compute the slope at which the cumulative distribution function changes. Now let's go back to calculus a little bit in terms of area under the curve. We're going to consider events. And the events for us will be actually delimited or defined with the help of two real numbers, a and b. So we could be looking at the event that the random variable x takes on outcomes smaller than or equal to b. That's going to be the union of two events. It's the event of the random variable x taking on values smaller than or equal to a, or the random variable taking on a value which is strictly greater than a or smaller than or equal to b. Now that's true in the discrete case as well, but in the continuous case, you don't need to worry about the type of inequality, whether it's strict or inclusive. That's because when you compute the CDF at a specific point, you are really computing the area under the curve. So what we're saying here is that the probability density function, you're saying that the probability that the outcome of the random experiment lies between a and b would simply be the area under the curve for the probability density function, here not the CDF, between a and b. And because we know that this little f is the derivative of big F, that the PDF is the derivative of the cumulative density function, then we can use the fundamental theorem of calculus this way. Okay. So when we want to compute this probability, the probability that x will take on outcomes between two values a and b, all we need to do is to compute the area under the PDF between a and b. So that's good for us because what it really means is that probability is applied calculus. And calculus is easy, at least it's easier than working with combinatorics. At least it's easier than working with the binomial coefficients, looking at combinations and arrangements, right? discrete probability is harder to work with in continuous probability because of the linear calculus. These probability density functions for continuous variables have a similar set of properties as what we had for discrete random variables. There's a few exceptions. The first one is that the PDF has to be positive, or at least positive for all values in the set of outcomes. It has to be at least non-negative. And the limit exists, right? The limit in both cases, whether you go to positive infinity or negative infinity, has to be equal to 0. Let me just give you a little chart here. Whatever the PDF looks like, can have funny things, but it's got to go to 0, because if it doesn't go to 0, you will not have the ability to have that the integral is equal to 1. It's not sufficient. I mean, you can have curves that go to 0, positive infinity and negative infinity, for which the area under the curve isn't finite. It isn't equal to 1. But if you want the area under the curve to be equal to 1, if you want the total probability to be equal to 1, you at least have to have that the limit of the PDF, positive infinity, negative infinity, should be 0. That is a horizontal asymptote. Let me re-emphasize that it is not sufficient for this pair of limits to be equal to 0 in order to have the total probability be equal to 1, but it is necessary. The difference here with discrete random variables is that for discrete random variables, you additionally have to have that the PMF value at any given point has to be smaller than or equal to 1. That's not the case for continuous variables. You can have a PDF which would take on very high values, right, over a very small interval. What matters is that the total area be equal to 1. And then finally, the way in which we compute the probability of an event, which is to say that the random variable's outcome will fall between A and B. As I've mentioned before, we simply compute the area under the curve. It doesn't matter if we have smaller than or equal or strictly smaller, because the area under the curve is not affected by whether we actually include the endpoints or not. For any value of x, the cumulative distribution function, it is, as mentioned before, the probability that the random variable will be smaller than or equal to x. And here you can use the fundamental theorem of calculus to recognize that we're talking about the area under the PDF from minus infinity to x. Just draw a little chart here. Let's say this is the PDF. Well, if you want to know the probability that the random variable would be x or smaller, you need to compute the area under the curve, and that's simply this area here. You can see why the cumulative distribution function has to be increasing. If I take a larger value of x, let me say I'm going to pick x star, well, in order to compute the probability that x is smaller than x star, I have to first compute the probability that it's smaller than x, so it's some value plus some other quantity right here, right? So the probability that x is smaller than x star has to be greater than the probability that it's smaller than x if it turns out that x star is greater than x. You don't have a choice. You just keep on accumulating probability. And if you want to compute a slightly different probability, the probability that your random outcome will be greater than some threshold. So if we go back to the curve, your x, perhaps you're interested in this probability. Well, from the law of total probability, we know that this would be 1, the total probability minus this region here, which is to say 1 minus the probability that it is going to be smaller than the threshold. And from the point of view of calculus, this would actually just be the probability. This is just going to be the integral from x to positive infinity of the PDF. Notice something here when we speak about the cumulative distribution function, the CDF. We want to use x as our variable to be consistent with the fact that we're using it as a variable for the PDF. Well, if you're going to be using the fundamental theorem of calculus to compute it, this cumulative distribution function, remember, you're computing the area under the curve from minus infinity to x, and the x actually becomes one of the bounds of integration. The rest here, this is just saying we're computing the area under that curve. We're going to use another variable named t in this case, but we could use anything. We just want to use something other than the x so that we don't get confused by the fact that there's an x in the upper bound or the lower bound in the other example here. And so we just call this variable t, okay? And as we've said, for any a and b, the probability of all of these will be the same. One exception here, if b is greater than a, this makes sense, but if b is not greater than a, if b is smaller than a, then the probability that a smaller than x smaller than b should be 0, right? Because it's impossible for x to be greater than a and smaller than b if b is smaller than a. But if you use the integration formula, you'll still be able to compute an integral here. It will be negative, right? So whenever you do get a negative integral, you're really thinking that this means that the probability is 0, because this is an impossibility when you're talking about integrals. As an example, let's say that we have a random variable x with the following PDF. It takes on the value 0 all the way to 0. Between 0 and 2, it takes on the value x over 2, and after 2, it takes on the value. This is the PDF. What this is telling you is that if you draw a random number according to this PDF, you are more likely to pick a number close to 2, smaller than 2, but close to 2, than a number which is close to 0. And you are completely unlikely, in fact, it's impossible for you to pick a number which is smaller than 0 and a number which is greater than 2. Okay. The first thing we'll notice is that the area underneath the PDF is actually equal to 1. I write here the integral between 0 and 2. In reality, it's the integral between minus infinity and positive infinity that is of interest to us here. But what we know is that before 0, there's no function to integrate. It's going to be 0. And after 2, there's no function to integrate. It's also going to be 0. The only place where something is happening is between 0 and 2. So we'll just write the integral between 0 and 2. That integral is equal to 1. You can flat out compute it, right? It's going to be the integral of x over 2 between 0 and 2. That gives you x squared over 4 between 0 and 2. You first replace x by 2. That gives you 2 squared over 4 minus what happens when you replace x by 0. Well, it's going to be 0 squared over 4, this is 0, and this is indeed equal to 1. If we want to compute the cumulative distribution function that corresponds to this function, we need to compute the probability that x will be smaller than or equal to x for all possible x's, x's varying from minus infinity to positive infinity. Now, let's go back and take a quick look at the PDF again. If x is any value before 0, the cumulative probability, the area under the curve, is going to be 0. And if x is any value after 2, that area has to be 1, right? Because you've already computed all of this area, which we knew was 1, and there's nothing else to be added. So if you have a function which is defined with levels, branches, when the time comes to look at the CDF, you know that on the first branch you should be getting a 0, and in the last branch you'd be getting a 1. Now I say this assuming, of course, that the PDF has branches that are zeros and zeros. If the branches in the PDFs are not zeros, then no, this isn't going to be the case. You're not going to be getting zeros and ones, right? You're going to look at it on a case-by-case basis. Any x value before 0 would give you a cumulative probability of 0. Any x value after 2 will give you a cumulative probability of 1. What happens if you pick an x value somewhere here, for instance? Well, then you're interested in computing the area underneath the curve from 0 to x. This is just the area of a triangle. You know how to compute that, right? If you are looking at this value here, x, so the base of the triangle is x. The height of the triangle is given by the function, it's x over 2, and so the area of the triangle will be x times x over 2, base times height, divided by 2. So x squared over 4, what you get here. Now in general, you're not going to be getting nice linear functions for your PDFs, and so you need to know how to compute this quantity, this area in the generic case. You do so by computing the integral of the function between 0 and x. So you integrate the function, which is, well, I'm not going to write it as a function of x here, I'm just writing it as a function of t. So if f at x is equal to x over 2, guess what? F at t is just equal to t over 2. So you integrate the function, which is t over 2. The 1/2 is a constant with respect to t, so I can take it out. So you integrate t with respect to t between 0 and x. You find the antiderivative of t, that's t squared over 2, with respect to t, obviously, here. And then you evaluate at x and at 0, you replace t by x, t by 0, x squared over 2 minus 0 squared over 2 times 1 over 2, which is a constant here, and that gives you, well, x squared over 4. I am here assuming that you remember how to integrate functions. I will not usually work out the integral with you. Just give it. You need to make sure that you remember how to compute these things. So what does the PDF look like? It looks like this triangle that I had drawn, and the corresponding CDF. Well, when you integrate a straight line, you get a parabola. This is what we're seeing here. This is the corresponding CDF. And I mentioned originally that you were more likely to get a value close to 2. This is given by the fact that the curve here is concave up. Less likely to get a value close to 0. If you had something that was the other way around, if your PDF had been this instead, then you would have seen something that looks like this instead. With the same probability density function, what's the probability that your random variable x would fall between 0.5 and 1.5? Well, you need to compute the probability that x is between 0.5 and 1.5, and that's just the area underneath the curve between 0.5 and 1.5. Or if you already know the cumulative distribution function, that's the same thing as f at 1.5, capital F at 1.5 minus capital F at 0.5. It's important here for you to remember that this isn't going to be the same as little f at 1.5 minus little f at 0.5. At least in general, it will not be the same. It could happen by accident, but that shouldn't be something to expect. Now, this will make sense if you know what the CDF is. If you have the CDF, it is easier to evaluate a function at points than to compute an integral. But if you do not have the CDF, if all you have is the PDF, the density function, then you have to compute it. Now we know what the CDF is. It's a function that takes on the value 0 before 0, 1 after 2, and between 0 and 2 is the function x squared over 4. So here we just replace x by 1.5 and x by 0.5. That gives us a value of 1/2. So there's a 50% chance that the outcome x will fall between 0.5 and 1.5, but with the understanding that it is more likely to fall above 1 than below 1. And now what's the probability that the value x is exactly equal to 1? Right? That's a midpoint between 0 and 2. So you need to compute the probability of the event. You need to compute the probability that x is equal to 1. We can rewrite this event, x equals 1, as the interval of all x values between 1 and 1. It's sort of dumb to do it this way at first glance, but you know, this is the same interval. Now we write it this way because we have a method to compute the probability of an event if you're given n points for an interval, a and b. You simply compute the cumulative distribution function at the higher endpoint and the cumulative distribution function at the lower endpoint, and you subtract the latter from the former and you get 0. Or in other words, you're computing the integral between 1 and 1 of the PDF, while the integral on the interval of length 0 has to be 0. It's a property of calculus. So perhaps that's unexpected to you, right? The probability density function at that point is not equal to 0. Right here, PDF is about 1/2, but the actual probability of getting exactly 1 is 0. That's what I meant when I was saying that the density function is not equal to the probability. It is only equal to a probability over like an interval when you integrate the probability density function. What this is saying really is that the probability that a continuous random variable x will take on any specific single value is 0. It cannot happen. Or at least we can't describe it with this paradigm. Right? So if we look back at what we had, we were looking at the area between 1/2 and 3/2. This little region here, it corresponds to these points. Subtract this one from this one, and get 1/2. It's important to learn how to read the PDF diagram and the corresponding CDF diagram. And we'll do another example here. We're going to assume we have some lambda value which is positive, right? And there's a random variable x which has the following PDF. It tells you how likely specific outcomes are according to the interpretation that I've given for the PDF, which is that the area under the curve between 2 points tells you the probability of the random variable falling between these 2 points. So we're not talking about a single value, which is a range of values. The PDF is given by this function, lambda exponential of minus lambda x if x is positive and 0 otherwise. I'll give you a little drawing. We'll see the computer drawing in a second, but we're talking about something which would be 0 prior to 0 and something that would look like this otherwise, after 0. The first thing we'd want to ask is, is it actually the case that the probability, the total probability here is 1, that the area between minus infinity and infinity is equal to 1. So as an exercise, you should verify that given that lambda is positive, you can convince yourself that the integral of this function from minus infinity to infinity is indeed equal to 1. Now, a question that we're asking is, what's the probability that x would be greater than 10.2? So let's say that this is 10.2. What's the probability that the outcome of the experiment will be greater than 10.2? You're looking for the area here. Or if you have the cumulative distribution function, well, you just need to compute an expression given by the cumulative distribution function. Now, in theory, what you're really computing is this thing. That's the area of interest to you, which, if you want, is going to be the same thing as 1 minus everything else that came before. Right? Because it is a probability density function and the total area is 1. And this thing here, this expression here, this is actually the probability that x would be smaller than or equal to x. It is given by the cumulative distribution function. Now, of course, that value depends on the parameter lambda. We haven't specified what it is, but if we pick different values of lambda, we will be getting different probabilities here. So how do we compute this CDF? Well, we actually integrate the probability density function from minus infinity to x. Remember here, because we are integrating all the way up to x, x is one of the bounds, you will want to write your probability density function using some other variable, in this case the t's. So the integral when x is smaller than 0 all the way up to 0, that's going to be 0. There's no area there at all. When x is greater than 0, then you're looking at integrating this chunk of the function with respect to t, when the variable takes on the value t, between 0 and x. So the lambda is a constant with respect to t, we can take it out, and then you end up having to integrate an exponential with respect to t. It's quite easy to do so. In fact, you'll be exponential of minus lambda t divided by minus lambda. That's the antiderivative, and then you'll be multiplying by lambda, so the lambdas will cancel out, and you'll only be left with a minus here. Again, if you're not sure, work it out. This is something you need to know how to do. You integrate, you evaluate at the two bounds, first at x, then subtract that at 0, and you'll get this thing here, this expression. So this actually measures cumulative probability, right? Goes to 0 when x goes to infinity, goes to 1 when x goes to positive infinity, and in between curve that actually follows is this one. 1 minus the exponential of minus lambda x. Then if you're interested in knowing what the probability that your random variable will be greater than 10.2, remember we said that it would be 1 minus the cumulative distribution function of 10.2. And so this is 1 minus the expression to evaluate. Well, we'll just replace x by 10.2 in there, and you will get the exponential of minus 10.2 lambda. So the probability that it's greater than 10.2 actually depends on what your value of lambda is. For instance, if lambda was 0.002, the probability that your x would be greater than 10.2 would be pretty high, about 98%. If lambda was 0.02, the probability would still be high, but slightly smaller, about 82%. The 0.2 value of lambda gives you a probability of 13%, and as lambda becomes larger and larger, that probability becomes smaller and smaller. If lambda is equal to 200, well, if you punch it in the calculator, you'll get 0. That's not exactly 0. It just means that we've run out of space to display the size of the quantity. It's minuscule, but it's not actually 0. Except if it's meant to define the likelihood of an event happening, it will not happen. It would never happen, even though it's not quite zero. So here's the PDF and the CDF for a specific value. I pick lambda equals 0.2. And these are the corresponding areas, right? You're basically computing not only the area under the curve, but you're seeing what the difference between the value of 1 and that corresponding value in the CDF at 10.2 is. So this quantity here, that's the thing that's about 13%, the difference between the probabilities. And if you pick lambda equals 2, for instance, well, you're interested in computing the area under the curve from this point onwards. Graphically, it looks like it's 0. It's not quite 0, as I said. Here, even here, if you were to look at the difference, it looks like the two lines overlap. They don't. In fact, the distance between them is this number, 1.38 times 10 to the minus 9. But visually, at least at that scale, it looks like it's the same line. It looks like there's no area under the curve. Except, well, it isn't quite. There's a difference. There's two lines here. This is their distance.